Welcome back, everybody. So we're going to go ahead and finish the 2.2 notes here. And so we're just working through those examples at the end. So for number 3, this is actually an extremely common type of AP question that you're going to see involving derivatives. We're going to be given a position function, and we're going to calculate some things about the velocity, and then we're also going to calculate distance traveled. So for this question, we've got our equation of our curve up here. So S is f of t, where we've got this cubic polynomial. Doesn't look factorable, so I would always check to see if it's factorable first, but it doesn't look like there's going to be an obvious factorization of this. So for part A, we want to find the velocity and then calculate the velocity at 3 seconds. So the velocity, again, is just going to be the derivative of position, so that's going to be f prime of t, which is going to equal 3t squared minus 18t plus 15. All right, so get that written here. So let me zoom in a little bit. So that's going to be our velocity at time t. So then f prime of 3 would be, let's see, so 3 times 9 is 27, minus 18 times 3 is 54, plus 15, so we're going to end up with, let's see, I think negative 12 as our velocity, and what seconds and feet are our measurements, so this is going to be feet per second, so negative 12 feet per second. Now the other thing I'm going to do though is I'm going to take my velocity and I'm going to factor it a bit. So we can take out the greatest common factor, which is going to be 3 between those terms. And I'm going to get t squared minus 6t plus 5, which is going to be very useful for the next step. So it says, when is the particle at rest? So at rest is kind of the key word there. If your particle is at rest, what is the velocity? The velocity is 0. All right, so at rest is asking, when is f prime of t equal to 0? And note we've factored our f prime of t as 3 times t squared, minus 6t plus 5 equals 0. So if we look at that and factor it a little bit further, we'll get 3 times t minus 5t minus 1 equals 0. So the particle is at rest at 1 and 5 seconds. And that's going to be really important. It's our particle's moving along a horizontal line, so we want to know when the particle's moving in the positive direction or negative direction. So if we're on a horizontal line, right, let's say this is position 0, then the positive direction is everywhere to the right of 0, and the negative direction is everywhere to the left. So what that means in general is in the positive direction means moving to the right. So we're moving to the right if we're in the positive direction, or moving to the left if we're in the negative direction. So how do we determine that? Well, one thing we do know is that the only time it changes direction are going to happen possibly at 1 and 5. So at 1 and 5, note this is f prime of t. We know that at those values, the velocity is 0. So at those moments, they are not moving left or right, which means that before 1, it's either going to be moving to the left or to the right. Between 1 and 5, it's going to be moving to the left or to the right. And after 5, it's going to be moving to the left or to the right. And there's no way you can have 2 different directional changes. right? So between 1 and 5, let's say that it's heading to the right until 3. Let's say it was heading to the right. And then from 3 to 5, it was heading to the left. Well, what would have had to happen at 3 if it's going to the right and then it's going to the left? It has to stop. But we know it can't have stopped because the velocity is not 0 at 3. So those 0 velocity locations are going to be where our turning points could possibly be. All right, so again, we know that f prime is equal to 3, t minus 5, t minus 1. So now we just need to check some values. And this factored form is really nice because all we care about is the sign. So if this is positive and positive, then we're positive on the interval. If it's positive and negative, then we're negative on the interval. If it's negative and negative, then we're positive on the interval. So we can just use what we know about the signs through multiplications. So let's think about f prime of 0. So if I plugged in f prime of 0 into that, I would get 0 minus 5 and 0 minus 1, both negative, meaning f prime of 0 is positive. So that means we're moving to the right. Oh, and we should actually indicate time is going to start at 0. So from the interval, on the interval 0, 1, our particle is moving to the right, which is going to be the positive direction. We can then look at f prime of 2. So you can pick any number between 1 and 5, but let's say we pick 2. Then still going to be negative here, but now we'll be positive, which means we're going to be moving to the left on that interval. So from 1 to 5, so 0 to 1, we're moving to the right, stops at 1, changes direction, goes back to the left. And then at 5, so let's pick 6, let's say. So then f prime of 6 is going to give us, obviously, positive, positive. So this is a well-behaved particle, looks like. It's changing direction every time. So there will be cases where it's always decreasing, or always increasing, or some other variation of that. So don't assume that it's always going to change from positive to negative, but it does in this case. So then, how do we explain this, right? This is all of our work, but for the AP standards, you have to be able to describe this behavior in a sentence, and so that's going to be pretty easy. So we would say that the particle is moving in the positive direction on the interval 0, 1, union 5 to infinity. So I don't know, let's double check our problem here if we stop at a certain time. I don't think so. It's just going to continue moving. So our domain is just t greater than or equal to 0. And then the important part, because we have to justify how we know that, your work alone is not justification. So the sign chart that I've made is really useful because you can visually see it, but you have to describe what that means. So we're moving in the positive direction because f prime of t is greater than 0 on those intervals. So key standard is that justification, which in this case is just, you just have to explain that f prime is positive if we're moving in the positive direction. And if we were doing in the negative direction, it would be the interval 1 to 5 because f prime is less than 0 on that interval. Okay. And now the last part, which is find the total distance traveled during the first 8 seconds. So for total distance, we have to be slightly careful. So there are 2 measurements that we'll be interested in. One is displacement. Oops. And one is distance. Sometimes those are the same, sometimes they're not. So displacement is just the change in position between points, between 2 points. whereas distance is the total number of units traversed between 2 points. Right? So displacement and distance can be the same if we're always increasing or always decreasing, right? So if a particle is just moving straight up or to the right, right, then its displacement and distance will be the same. However, if we look at our particle is moving to the right from 0 to 1, to the left from 1 to 5, and then to the right again after 5, which means that the minus portion here, if we just look at the displacement, is going to subtract from the actual location. So for distance, it always has to be positive. So we need to make this distance traveled from 1 to 5 into a positive quantity. So that's what we're going to need to do, is any negative distance measurements, which will be useful for displacement, will not be useful for distance being traveled. So let's go ahead and figure it out. So the first 8 seconds, so we'll just note that our particle is moving to the right on 0, 1, to the left on 1, 5, and then to the right on 5 to 8. So we're actually going to close our interval because we only care about up to the first 5 seconds. So what that means is from 0 to 1, we're moving to the right. But from 1 to 5, we're moving to the left. And then from 5 to 8, we're moving to the right. So what we want to do is we want to measure each one of those lengths traveled and then add them all together. All right, so this total length will be distance. Okay. So for the black arrow and the red arrow, those are going to be positive. But the blue arrow is going to be negative, which means I need to flip it around. So the way that we're going to calculate this then is that the total distance is going to equal the change in position from 1 to 0 plus the change in position from 5 to 1, from 1 to 5, plus change in position from 8 to 5. Now you'll notice I've added absolute values here because I want my answer to always be positive. I actually don't need absolute values on these first two, but in general, as long as you know where the change of position is, if you take the absolute value, you'll guarantee that your answer will be positive. All right, so then we just need to calculate our total distance. Now that's going to be from our original f of t. So we'll note that f is going to be t cubed minus 9t squared plus 15t plus 10. So we're not using f prime here because we're measuring distance, which is going to be the change in position. So then we just need to calculate each one. So let's go ahead and work that out. So f of 1 and f of 0, so f of 1 is going to be 1, actually, why don't we just put this into Desmos. So we'll do f of x equals 3x cubed minus, what was it, 3x cubed? No, just x cubed, sorry. Minus 9x squared plus 15x plus 10. So there's our position function, which we can see over here on the left. And we can see our changing of signs. Whoops. So changing sign at 1, changing sign at 2. So we can see that the particle is moving upward from 0 to 1, all the way down to negative 15 from 1 to 5, and then all the way back up. So we'll want f of 1, which is 17. Okay, so that's going to be 17 and then minus 10, which is 7. F of 5 is negative 15. So negative 15 minus 17, which is equal to 32. And then f of 8 minus f of 5, so f of 8 is going to be 66. 66 minus negative 15, which is 81. So it looks like 81 plus 32 plus 7, which is 81 plus 39, which I believe is 120 feet. Nice even number. Awesome. All right, so we traveled 120 feet on that interval. Now, suppose we wanted the displacement between 0 seconds and 8 seconds. So in that case, we would actually just do, so for displacement, that would just be f of 8 minus f of 0. So f of 8 was 66, f of 0 was 10. So 56 feet is the change in position from the particle at 0 seconds to the particle at 8 seconds. And note, 56 is much smaller than 120 because we've subtracted a bunch of distance where we were negative. So we were negative both on the interval 1 to 5 as well as a portion of the interval from 5 to 8. And that distance that we were negative on is going to account for the difference in that distance measurement from the displacement measurement, which looks like it's about 64 feet difference. All right, good. So we've got 2 more here, so I'll discuss these pretty quickly. So for what values of x does the function have a horizontal tangent on the interval 0 to 2 pi? So horizontal tangent is another buzzword that we'll see quite a bit. So our tangent is horizontal if y prime is 0, right? So the derivative of y is equal to 0. So let's go ahead and differentiate this. So dy dx is equal to derivative of x is 1. And then, if you remember, cosine we derived earlier is equal to negative sine x. So this is going to be plus 2 sine x. And then equals 0. So that's going to be the same as sine x is equal to negative 1/2, which means x is equal to arc sine of negative 1/2. So let's go ahead and figure out between 0 and 2 pi where x is going to equal that arc sine value. So negative 1/2 is going to be at 7 pi over 6 and 11 pi over 6 in the 3rd and 4th quadrant with reference angle 30 degrees. And I think that's it. And again, you can double check that by substituting in. And note I use the dy dx here, but I could have just as easily said y prime. So don't be afraid to mix the notation there. And really, this one's going to be important because dx is what we normally use for functions of x, but we're also going to have functions of t for time. So when we do that, we're going to have to use what we call implicit differentiation, which we will look at in section 2.5. All right. So then for number 6, it says draw a diagram to show that there are two tangent lines to the function y equals x squared that will pass through the coordinate 0, 4, whoops, 0, negative 4. So let's go ahead and sketch a little rough graph here. So there's y equals x squared, 0, negative 4. It's going to be somewhere down here, so this looks pretty obvious. Let's see if I can use my drawing tool here. So there's going to be a tangent line there. And there's going to be a tangent line over there. So we can see that there's going to be two tangent lines that, again, pass through that same common coordinate of 0, negative 4, and then some points on our parabola. This picture is actually slightly off because those points should actually be symmetric in this case. So they will actually be symmetric. That won't always be the case depending on the curve. So it says find the coordinates of the points where the tangent line intersects with f of x. So the question is what are these coordinates? All right, so let's give them a name. Let's say A, and this is going to be negative A. So this is a comma a squared. So we only need that first one, and we can actually find both, I think. So we've got f of x equals x squared. So f prime of x is equal to 2x. But note, on our tangent line, we have the coordinate 0, negative 4. And we have the coordinate a squared and a. So we know that f prime of a is going to equal 2a by our derivative. But f prime of a is also the slope between those 2 points, which we have the formula for as well. So we also know that f prime of a is going to equal y2 minus y1 all over x2 minus x1. So we got that. And again, that's going to equal 2a. So it looks like we have a squared plus 4 over a equals 2a. We can do a little bit of algebra with that. So let's scoot that up here. Multiply both sides by a. And then subtract the a squared over. So it looks like 4 is equal to a squared, which means a is equal to plus or minus 2. Which means that our coordinates are going to be negative 2, 4, and 2, 4. So those are our 2 coordinates based on our work there. So 6 is a really good example of extending our understanding of the derivative, specifically with graphical representations of the tangent line and a curve. So you're going to see this in your homework as well. All right, so I think that concludes the notes there. So again, if you have any questions, feel free to shoot me an email and come by the office hours. But otherwise, until I see you next time.